We now need to talk about floating point representation of numbers, which is critical to understanding how computers actually store and operate on numbers. First of all, I want to show you an idea that we'll have to adopt anyway, and this is something that will work in the decimal form as well. The idea is that you only have one significant digit before the dot in any representation of a number, and that is sometimes called scientific notation. So instead of writing 6,519.23, for example, what you would do is you would write it so that there is only one digit before the dot, so you would have 6.51923 multiplied by 10 to the power of 3 in this case. And similarly, if you had a very small number, let's say you had 0. And then 5 zeros, 391, you would actually change this into 3.91 times 10 to the minus 6. So hopefully the idea is clear, and if you look at, let's say, the calculator that's built into your operating system, you'll see that it has a scientific mode which represents all the numbers in the following format. Okay, so what is it, and why does we have to concern ourselves with it when we're talking about floating point representation? Well, the thing is, the computer also wants numbers in this format. So the computer essentially is looking for something like the following. It's looking for a number which has a 1, and then there is a dot here, and then the fractional part, which would be just a bunch of binary values, multiplied by 2 to the power of, and then a few more binary values. And once again, when I write B, that's a bit. So that's either a 0 or a 1. So in this form, we give names to the different parts that we're defining. And those two parts are the mantissa and the exponent. So essentially, this part is called the mantissa. And this part is called the exponent. And all the numbers that the computer stores are actually made up of these two parts. But it's not as simple as that. So let's take a look at the way that the computer actually stores this. But before we do, I want to give a brief explanation of how we arrive at the binary representation. How do we actually get any number in the following form? So for example, let's suppose that I have the value of 50. And I want to get it in the form 1 point something something something. What I can do, and this is a bit of a trick, is I can divide it by 2 to the power of something, and then I can multiply it by 2 to the power of that same thing. Now remember that I'm generally looking to have a 1 here in the lead, so I can't divide it by 2 to the power of 100, for example. It doesn't make any sense. But I can divide it, in this case, by 2 to the power of 5. And the reason for that is 2 to the power of 5 is equal to 32. So if I do that, I will get a number which is greater than 1. But on the other hand, I will not get a number that's too small here on the left. So this would be 50 divided by 2 to the power of 5 and then multiply by 2 to the power of 5. Now it might seem like a bit of a pointless exercise, but if you think about this representation, it should make sense to you why we're doing this. Because basically you take this part and you evaluate it, and in decimal form it will be 1.5625, and then the part on the right, so we already know what the exponent is, so this is going to be multiplied by 2 to the power of 5 because that's what we have here. And then we can jump into the binary form. We can represent this value as well as the 5 in terms of bits. So we can say this is actually 1.1001 multiplied by 2 to the power of 101. Okay, so this is a simple example. Let's take a look at another example. Let's suppose you want to represent the value 0.3125. I'm specifically choosing values which have a nice binary representation, but this one is a bit tricky because to get a 1 here, instead of dividing by 2 to the positive power, we have to divide by 2 to the negative power. So in this case, it makes sense for us to divide by 2 to the minus 2 and then multiply by 2 to the minus 2. So this would be in, once again, in base 10, this would be 1.25 multiplied by 2 to the minus 2. Or if we jump to binary, it will be 1.01 multiplied by 2 to the minus 10. And you'll notice that there is a minus here. Now, how can this be? I mean, the computer does not have an ability to store a minus. It can only store ones and zeros. It cannot store this minus here. So we have to deal with this particular situation. And in fact, this is what floating point representation actually does, is it tries to deal with this situation of having negative numbers as well, because numbers can be negative. So how does it do it? Well, essentially, given a chunk of memory, it simply allocates different parts of memory for storing different things. So let's try drawing just a chunk of memory, just an allocation of bits, essentially. All right, so here is a chunk of memory, and we subdivide this memory for various things. And two obvious things that we have to allocate memory for are the mantissa and the exponent. But it's not as simple as that, unfortunately. What we do is we first of all allocate a single bit, so a single 0 or 1 bit, and we allocate it for the sign. The sign. And that's the sign of the number as a whole, which immediately raises the question, well, what about this sign? How come we've forgotten about the sign of the exponent? So we have the sign of the mantissa, but we don't have the sign of the exponent. That doesn't seem to be fair. And I'll explain it in a second. So essentially, whatever we've got left, and that can be, let's say, 63 bits, we can allocate it to the mantissa and the exponent. So we can say, okay, let's subdivide this. So let's have this part as the mantissa. So the mantissa, this can be, let's say, 52 bits. And then for this part, we have the exponent. However, there is no sign bit for the exponent. Instead, what we do is we use something called a bias. And this part, by the way, is 11 bits. So we have 52 plus 11 plus 1, which is equal to 64. So essentially, the mantissa part is fairly obvious. The sign bit is fairly obvious, but the exponent and bias is a bit confusing. So we've currently allocated 11 bits to the exponent. And if we take these values as whole values, then they would be values going from 0 to 2047 inclusive, because that's how many bits we actually have. However, instead of doing this, we need to concern ourselves with this situation, the situation where the exponent can actually be negative. So instead of using this range, we essentially add a bias. So we say that we're going to use a bias value. And in this case, the bias value is somewhere halfway down this range. So the bias value of 1023. So what this means is that instead of having the number represent the exponent exactly, we have this number, the number that's being stored here, and then we add 1023 to it. And this gives us a completely different range of possible exponents, because instead of having the exponents from 0 to 2047, we have exponents from negative 1023 all the way up to 1024. So we have a different range of values, and this range accommodates negative numbers. So that's what we're doing essentially here. Okay, so another little bit of confusion here is that the terminal values, so the value minus 1023 and 1024, are actually used for other things. And those two other things are infinity and not a number. So infinity and not a number. And infinity and not a number are important concepts as well. To kind of simplify the explanation, if you have 1 over 0, that gives you an infinity. Or if you have any kind of number over 0, if you have 2.5 over 0, that gives you an infinity. Of course, if you have minus 1 over 0, that gives you a negative infinity. Negative infinity is also a concept. And whenever you have something like 0 divided by 0, or you have infinity divided by infinity, that's why you get something called not a number. And not a number is a viral thing, meaning that if your calculation has a nan result somewhere and you're using this result, then everything else, all the other calculations involving this nan, are also themselves nans. So it's very important to take care of this if you're doing any kind of calculation which risks dividing by 0, for example. Okay, so now that we're in agreement about how to store numbers, we can actually take a look at how to represent a particular number. And of course, for that, we need to make a decision on how many bits we allocate. For this, there is actually a standard. There is a standard called IEEE 754. And essentially, it mandates two different sizes of floating point numbers. There is single precision and double precision. Single and double. So single precision uses 32 bits and double precision uses 64 bits. So let's suppose that we decide to use the double precision in order to store a particular value. Let's say we want to store the value 22.5. So 22.5. We need to somehow convert it into this notation using all of the things that we've described above. So first of all, we need to normalize the number. Remember, we want one significant bit in front. So essentially, we take 22.5, we divide it by 2 to the power 4, and we multiply it by 2 to the power 4, which gets us 1.40625. 1.40625 multiplied by 2 to the power of 4. Okay, so in double precision, the exponent, will take care of the exponent first of all. So the exponent is 4, but let's not forget about the bias. So we say 4 plus the bias is equal to 1027. And 1027 is going to be stored as 1, lots of zeros, and then 1, 1. Okay, so this is essentially our calculation for the exponent. Right, and then the mantissa, which is this part, so the mantissa doesn't actually include the 1. The mantissa is just 0.40625. We don't care about the 1 here because the 1 is essentially implicit. It's part of the number. It's assumed to be part of a number. So this is stored as 0.01101, 000, and then lots of zeros. Okay, so we can now draw the layout of the overall storage of this whole thing. So let's draw it like this. Okay, something like this. Okay, so the sign bit is 0 because that's the sign. Our number is positive, so we don't need the sign. And then here comes the exponent. So let's have the exponent from here to here. So the leading digit of the exponent is a 1. And then we have a bunch of zeros, and then the 2 1s here. 1 here, and 1 here. So this is the storage for 1027. Because 1027 happens to be 1024, which is this bit, plus another 2 plus another 1. So that's 1024 plus 2 plus 1, which is equal to 1027. That's exactly what we get. And then the mantissa, obviously. So that's 0, 1, 1, and then lots of zeros. Okay, so that's the mantissa. All the values here are zeros. throughout this whole thing. And then, of course, the assumptions that we've made, of course, is that once again there is 1 bit here, and this whole thing, this part is 11 bits, and the rest is 52 bits. And this is how you get a floating point representation of a number.